outer space, humanity's final frontier, the last great horizon. We voyage into the endless black almost all the time these days, and very few people are aware at any given moment how many humans are up there orbiting right now. That number has always been above zero since the dawn of this century. We associate names like Dragon, Soyuz, and Apollo with the highest standards of safety and reliability. So mundane and trustworthy that you can count on one hand the number of times these systems have endangered human lives. And when that does happen, it becomes a worldwide news phenomenon. And yet, not so long ago, outer space was a horizon beyond which no living being could ever cross. Names such as Albert, Gordo, and Laika all would give the final and ultimate sacrifice in humanity's race to simply survive the harshest conditions we had ever known. Despite the hurdles and the mistakes, as time progressed, we improved, we corrected, and we learned. The beginning of humanity's direct forays into outer space can be marked down to one single day, April 12, 1961, when the Soviet Union would propel a then unknown Yuri Gagarin into orbit of the Earth and into history. Vostok, the large metal ball that served as Yuri's precious bubble of life, incorporated several aspects and design choices that seem today quite dangerous. Whilst being reliably navigated by the means of early and impressive Soviet computers, many other systems were rushed and left much to be desired. It had no safe landing capability, and beyond the onboard ejection seat, the use of which was mandatory at the end of each mission, it would feature no other launch escape mechanisms to save its pilot in the case of a launch vehicle failure. The American effort had no clue of these Soviet shortcomings, and assumed that the USSR had cracked the code of vehicle recovery from space. It would take an ensemble of some of the finest minds of a generation, handpicked from all across the nation, to match the engineering challenge that the Soviets had masterfully framed. Back in the fall of 1958, at the Langley Research Center in Hampton, Virginia, a team of engineers would set their own historic date. It would be them who would design the American spacecraft, and it would be their work that was on the line. A daunting challenge, the newly dubbed Project Astronaut was up and running. And hopes high, all they had to do now was to make sure it worked, as science and lives demanded, and to test. Test, test, test. Big Joe, Little Joe, the Redstone and Atlas rockets, capsule shapes, electronic systems, hands-on control systems, parachutes, ablative heat shielding, recovery mechanisms, and life support. All of these systems could be tested and refined to the absolute limits of the day's technological potential. In the midst of this testing, and by presidential decree, it would gain a new name, Project Mercury. Eventually, with a design chosen and the successful Soviet flight of Vostok 1, the test flights and tinkering had to come to an end. On May 5th of that year, this time it would be for real. A true flesh and blood human of the highest order named Alan Shepard would be in command. Design teams, NASA, and the United States government held their breath. Would the systems all work? Or would the United States have produced the world's first dead astronaut? As the countdown clock closes in on Freedom 7's 15-minute flight, there is only one way for the world to find out.
All right, lift off and the clock has started. Yes, sir, reading you loud and clear. This is Freedom 7. The fuel is go. 1.2 G. Cabin at 14 psi. Oxygen is go. Freedom 7 is still go. This is 7. Fuel is go. 1.8 G. 8 psi cabin, and the oxygen is go. Cabin pressure is holding at 5.5. Cabin holding at 5.5.
I can understand. Cabin holding at 5.5.
The fuel is go. 2.5 G. Cabin 5.5. Oxygen is go. The main bus is 24. And the isolated battery is 29.
There is a saying, what goes up must come down. Shepard's mission ticks by, and after just 5 minutes of weightlessness, it was time for the Mercury Capsule to do just that. While safely reaching space and with the life support holding, G-forces are beginning to build up, and the spacecraft begins to shake. The retro pack has fallen away, and the intermittent bangs of reaction control system firings are heard as Mercury wrestles to maintain attitude control as it falls back to Earth. Atmospheric reentry. Streaking across the sky at over 8,000 kilometers per hour, or Mach 6.7, the tension grows even higher. Any small defect in the capsule or its heat shield could easily end in Shepard burning alive. With Mercury descending and radar tracking teams racing to intercept NASA's man-made fireball, no one knows what will happen. If the American space program is to survive, it is now or never.
This is 7, go ahead.
We have something to transmit at this time, over.
The negative, just relaying my condition is still good. I'm good.
As the agonizing minutes pass, a faint voice is heard over the radio as helicopters rush in. It is Alan Shepard. He is in one piece, conscious and doing well. Recovery teams spot the Mercury capsule at a distance of 302 miles downrange from Cape Canaveral. The Mercury capsule is bobbing in the ocean, afloat and okay. Helicopter recovery teams successfully retrieve both spacecraft and pilot. The mission to put the first American in space had been flown to near perfection, and Alan Shepard, alongside his fellow astronauts known as the Mercury 7, would be revered as legends to this very day. Although their accomplishments are well known in popular media such as The Right Stuff, and in videos and documentary films right here on YouTube, very little is mentioned of the engineering, design, and technology that enabled Mercury's success. That ends today. My name is Jackson, and my channel, Homemade Documentaries, and this one, share a deep passion to educate, preserve, and remember spaceflight history for our generation and for those who come after us. So here's my friend Ben, the driving force behind Retro Rockets, to tell us a little bit more about the Mercury capsule, the machine that made the men.
Hello everyone, Ben here. First, a huge massive thank you to Jackson from Homemade Documentaries. If by some miracle you haven't seen his incredible videos, drop this and go watch his Mercury video first, as it sets the stage and tells the actual story much better than I ever could. A link to his video will be right on up there in the description, and don't worry, I'll wait. Secondly, for those new to the channel, welcome to Retro Rockets, my little one-man project where we go over the features, specs, and technology on all sorts of forgotten, and in this case, not so forgotten spacecraft. We'll take a good look at what's inside these machines and see what made some successes, and others failures. With that out of the way, and speaking of details, since I haven't covered it yet, let's briefly go over the rocket, or launch vehicle of the Mercury program. Well, one of them at least, the Redstone M. Being one of the last variants of the Chrysler-produced Redstone, the Redstone M was basically, dare I say it, a big old scaled-up and advanced V-2 missile. It would run on a somewhat waning ethyl alcohol and liquid oxygen-based system, and its Rocketdyne A7 engine could produce a maximum of 78,000 pounds of thrust. It ran on a 60-volt electrical architecture like some giant 60s cordless lawnmower. And just like the V2, it would see it using a gyroscopic internal reference system, as well as its fuel tanks being extended for Mercury flights. It would feature a full water recovery system complete with parachutes and all, and although no Mercury Redstones were ever reused, it's a little fact that I found to be rarely mentioned. Also similar to the V2, it would use a gas generator to spin its turbopumps. But instead of using potassium as the V2 did, it would do so using steam from decomposing hydrogen peroxide. While most of us know the Redstone and it has widely available documentation, I feel it should at least be mentioned that the decision to initially choose the Redstone would come down to two things: development and safety. Even if the Redstone couldn't make it to orbit, this was still 1961. At the time of Freedom 7's launch, and especially during Mercury's development, the two-stage systems such as Atlas and Thor were blowing up all the time. And I mean all the time. Even if the Redstone was kinda meh, the decision was still understandable when things like this were still happening.
The first few seconds of the shoot go without incident. The Centaur climbs to 30,000 feet. Then, malfunction.
Ah yes, speaking of our explodey boy, the Atlas. I've covered a few other variants of it in my other videos, So for this, all you need to know is that it had no upper stage and was pretty close to the original Atlas, with some kinks being worked out, of course. However, it could still put the Mercury capsule into a low Earth orbit, and would do so successfully in the final 4 manned Mercury flights, with the first 2 missions going to the Redstone. One final thing to note about the Mercury Atlas was that, before manned flights, the Atlas D variant that was used was extensively looked over and tested to achieve its manned rating. Considering all manned Mercury Atlas missions were successful, I think it's fair to say that the teams did their due diligence. Alright, so now that we know what carried Mercury up to the stars, it's time, as always, to open this thing up and check out what makes this incredible machine tick. To preface the design section, I just want to note that to fully cover the Mercury experience, we are going to be going off the specifications of Capsule 16, internally known as the Mercury Model 133K, used for the mission Sigma 7 that took up Walter Wally Schirra for his 6-orbit trip. This is the latest craft I can get in-depth details for, and it should give us a decent benchmark of the Mercury capsule's capabilities at their full and final potential. There was quite a few small changes as the Mercury craft progressed, so if some of the specs or details are a bit off from what some of you remember, this is most likely the reason. As well as this, it should be of note that most of the diagrams you'll be seeing come from the good old May of 1962 revision of the Mercury Familiarization Manual, which covers a 3-orbit trip of the Model 133 spacecraft. It is the most representative document I could find for visuals, so just keep in mind that some photos might not be 100% spot on, but I will include as much narration info as I can from the Capsule 16 specification document. There will also be links in the description to both of these documents just in case you'd like to know even more specifics than I already cover. Alright, with those little disclaimers done, let's deep dive right into this thing. Being originally conceived of and designed by the famous Max Faget and his team, the later and refined Model 133K of Capsule 16 would see it weighing in at a grand total, with fuel and pilot, of 3,367 pounds, or 1,527 kilograms. It was constructed by the McDonnell Aircraft Corporation and would measure 10.8 feet long and would have a max diameter of a little over 6 feet. It comprised components from around 500 companies from all over the nation, and would be assembled at McDonnell Aircraft's assembly plant located in St. Louis, Missouri. Its main inner frame would be constructed primarily out of aluminum and fiberglass. However, externally these materials would be pretty garbage when it came to reentry heat. For this reason, the exterior panels of Mercury, the ones with all the iconic little shingles on them, would be made from an exotic material known as Rene 41. This metal alloy would be comprised of the following: 14.3% nickel, 19% chromium, 11% cobalt, 9.7% molybdenum, 3.1% titanium, 1.6% aluminum, 0.09% carbon, and a little sprinkle of 0.005% boron, with the remaining 2% or so comprising of iron. Not to go on too much of a tangent here, but this extremely exotic material was most likely very costly to produce, and it is my guess that this cost was the primary reason we see craft such as Apollo use honeycomb stainless steel ablative panels later on. Speaking of those Mercury panels, what did those louver of shingle things even do? Were they like cooling it down or what? At first glance, and being a racing fan, that was my first guess. Although, much like the early afterburners for McDonnell and various other aircraft, this was actually to prevent warping of the Rene 41 as it heated and cooled rapidly throughout the flight. In addition to these panels, this cylindrical section of the craft, the place where the highly heated shock cone of reentry would be a little too close for comfort, would be comprised of 0.2 inches of pure beryllium. While we're still on the subject of beryllium, it's a perfect time to talk about the ballistic heat shield, or should I say shields, of the Mercury spacecraft. So, the heat shields are one major development change to Mercury that I have to mention. As seen in this footage, originally in testing, a beryllium heatsink system was the go-to for Mercury, and it had pretty good ablative properties, not too slow, not too fast, as well as wicking away a massive amount of heat. This original heat shield design would make it all the way to the production phase, when, with the flights of the Atlas-equipped Big Joe, a new resin-based system was found to be the better option. This new heat shield was made from special layers of fiberglass cloth that were impregnated with phenol formaldehyde resin, otherwise known as simply phenolic resin. Just like with many things about Mercury's development, different ways of doing things were being tried and tested all the time. And when the resin heat shield was recovered from Big Joe 1's boilerplate test capsule, it was found that, surprisingly, this ablative heat shield didn't really ablate much at all, wearing at most to only 20% of the shield's total thickness, which altogether was only around 1.5 inches deep. On top of this, even with the lack of ablation evident, thermal penetration and heating of the craft remained relatively unchanged compared to what it should be. It was found that a thin layer of black charring to the shield counterintuitively radiated much of the heat away from the spacecraft, and in fact was its primary heat dissipation method. However, even with this discovery, further testing and production time was needed for the new resin-based heat shield. So, with the older shields in production and with Mercury being rushed into the limelight, it would be Al Shepard and Gus Grissom who would fly with the early model beryllium-based heat shields. Thermal insulation for the rest of the Mercury capsule would be done using materials such as ceramics, more fiberglass, Thermoflex, a nifty material whose thermal conductivity decreases with pressure loss, and a cutting-edge microporous material known as Min-K. In addition, Mercury would also feature a total of no less than 84 thermocouples to monitor heating throughout the craft, with some more advanced sensors even extending into the heat shield material itself. The main internal sphere of the Mercury spacecraft, called the inner pressure vessel, as well as its bulkheads, were also constructed with Rene 41 lined with an outer layer of pure titanium. As well as this, a pure titanium outer pressure vessel called the large pressure bulkhead would be both bead and seam welded to the inner pressure vessel. So, because it doesn't really fit into the design sections, I should also mention the good old landing skirt here. It was this bag-like contraption that was placed in between the heat shield and the bottom of the spacecraft, and when released by nitrogen actuators from its own little 3000 psi air tank right here, it would be used to cushion impact forces on the water, or in the extreme case of an emergency ground landing. It would feature no gas cartridges or anything like that, and when landing would simply just use the weight of the heat shield to pull in surrounding air through these small holes. As well as this, the landing skirt would also allow that big and heavy heat shield to act somewhat like a boat's keel, using its mass to keep the Mercury capsule upright while in the water. It is also not lost on me that to get around the whole ejection seat thing Vostok had, engineers for Mercury just slapped a big-ass airbag on this thing and called it a day. Mercury would also have one of the first space windows, being installed because, well...
Where are you planning on putting a window? Window? There's no window.
They wanted a window. This 3-pane individually sealed multi-layer window would incorporate an image suppression filter to negate mirror images, have its outer layer made from curved Vicor glass, and would feature a pure titanium housing. One other notable external section of Mercury was this small section on top of the spacecraft known as the antenna fairing. It, fairinged the antenna, and would jettison with the deployment of the main parachute during a normal mission, or with the launch escape system in case of an emergency. We'll get into what other stuff was actually inside the antenna fairing throughout the video sections, but it did have this one thing called the destabilizer flap. However, it also made sure the capsule's attitude was correct during re-entry or aborts, so it kinda sounds a lot like it stabilized something. Anyways, I'm sure somebody will explain that one to us in the comments. Another interesting fact to mention about Mercury's design was its motor and system lubrication. Due to its biological occupant, there would be zero use of petroleum-based lubricants and none could emit any toxic fumes, or become flammable in the case of bearing failures and the like. These lubricants consisted mainly of silicon and dried film-based types, as well as some special blends such as Fluorolube and Oxylube 702. Before we advance to the next section, I should also very briefly mention those capsule shapes. I don't want to get too deep into development here, but it should be noted that around 70 different shapes were tested before finally landing on the iconic geometry that we would end up seeing with ground testing and main flights. As we move on to the various tech and systems of the Mercury spacecraft, I hope it will become apparent that around a fourth of this vehicle's volume was taken up simply doing two things: keeping its pilot alive, and also not killing him from the bazillion things that could go wrong with this thing. Being from the very beginning of manned spaceflight, by modern standards, Mercury is almost over-engineered due to the sheer amount of unknowns faced at the time. As a certain someone once said, a very small and minute detail could be the difference between success and failure in space. Now about those details, let's get into those, shall we? The electrical power system for Mercury was fairly extensive and capable considering how small it was. The whole system would run on 2 electrical buses, the main bus and the secondary bus. After being fed through the buses, power would then flow to 2 separate fuse panels, and power loads on the spacecraft would be categorized into essential loads and non-essential loads to give pilots a good idea of what to turn on or off in any situation. Unlike my previous videos that cover unmanned systems which use automatic power systems, the vast majority of Mercury's was controlled by the pilots themselves. Even though Mercury had some low-power automatic switchgear for its non-essential electrical bus, it will become very clear over the course of this video that in a lot of ways, the computers for Mercury were the astronauts themselves. Moving on to the batteries, Mercury Capsule 16 would feature a total of 6 batteries across 3 separate systems: the main power supply, the standby power supply, and the isolated supply. Starting with the main power supply, we would see 3 batteries with a capacity of 3,000 watt-hours each. Today's equivalent of each battery would probably be around the size of a medium power station you would see for a long camp trip such as this one shown on screen. They and all the other battery systems would be wired in parallel and output a nominal 24 volts, with a maximum full charge outputting 29 volts, and with its low power cutoff tripping at around 18. As the name implies, the main power system would go on to power just about all of the spacecraft's systems. The standby system would house 2 somewhat smaller 1,500 watt-hour silver zincs, and could be used to power the whole of the spacecraft systems for a little over 1 orbit, or around 88 minutes. In addition to orbital power, the standby system would also contain enough power for 12 hours of post-landing power requirements such as radio systems. Now we come to the isolated battery system. It would consist of the one last remaining 1,500 watt-hour silver zinc battery, and would be primarily used for the pyrotechnic systems. We'll go over some of the more relevant pyro devices later in the video, but for now I'll just mention that this isolated system gave that little bit more reliability and redundancy to Mercury, as any problem with the main or standby system could not interfere with these components. This isolated system would also be what powered the automatic launch abort system as well as the launch escape tower. In the very unlikely but still present situation of a "Houston, we have a problem" moment, the isolated system could indeed be used to energize and power the whole spacecraft by manually switching it into the standby systems. This would require the pilot to work the capsule extensively to keep it in a low power state, but it was a feasible option and functioned as a last line of defense to keep Mercury operational in an extreme emergency. All of these previously mentioned batteries also featured diode-based reverse current protection to prevent a failed battery from leaching power. Now, while being rechargeable and able to be topped up by the ground umbilicals before liftoff, one small problem with silver zinc is that it tended to be, well, a little bit gassy. Specifically, that was hydrogen gas. With the unmanned craft I have covered, this wasn't much of an issue. Just let it vent to space and call it a day. With Mercury, though, because of its 2 birds with 1 stone type design, that being one where the pilot and systems share the confines of the temperature-controlled pressure vessel, this wasn't the case. Because of this, each battery would actually have its own little teeny tiny venting tube winding through the capsule, ending up at the lower section past the bulkheads, and venting this hydrogen overboard somewhere right above the heat shield. I should mention that up until now, I have only been covering basic DC circuits and systems. Much of Mercury, such as gyros and fans, needed that nice clean AC power. This would be accomplished by the means of the then bleeding-edge technology of static inverters. The main AC systems would use 2 of these inverters, with another one being used as a standby. All 3 static inverters would output 400 cycle or 400 Hz, 115 volt single-phase power. Just like some other things on Mercury which we will get to later, All three inverters were water-cooled by Mercury's Environmental Control System, or the E.C.S, and even had an added air duct for even further cooling. The main 250 volt-amp inverter would power the Automatic Stabilization Control System, or ASCS, direction rate and humidity indicators, horizon scanners, and the cabin lighting. The other smaller 150 volt-amp inverter in the main system was to be completely dedicated to just running the E.C.S. Even if those failed, as early static inverters tended to do at the time, there was still a redundancy in another 250 volt-amp inverter in the form of the standby AC system that would take over duties of either or both the main inverters if such need arises. Altogether, on average, Mercury would draw around 500 watts or so, with peak loads being 1 to 2 kilowatts, or about the draw of a small space heater set to high. As a last tidbit, or as Doug DeMiro would say, quirks and features of the Mercury electrical system, was that it cannot be overstated that because of the oxygen-rich environment of the capsule, every single electrical connection within it must have zero exposed wire or energized metal, as to not create any chance of shorting or sparking. As many of us now know today, this task was much easier said than done. A select few, yet noteworthy design choices pioneered by Mercury, those that were mainly intended to be a stopgap due to weight and development limitations, would unfortunately become adopted as tried and true designs. While Mercury is 100% an engineering marvel, I cannot bring myself to talk about this feature without briefly mentioning that it would be the early success of this inherently flawed idea to combat the fire hazard of pure oxygen, with painstakingly covering and maintaining no exposed connections that would eventually culminate in the Apollo test fire that ended up killing the previous Mercury Redstone 4 pilot of Gus Grissom. Well, that and the hatch, of course. On a lighter and more safer note, there is a very good reason why we luckily don't see pure oxygen manned systems anymore, beyond the necessary exception of spacewalk suits. Alright, with my rambling out of the way and getting back on topic, let's talk panels and periscopes. So, usually this would be the instrument section, but because there's a dude in here and all the stuff to support him, the Mercury capsule didn't have anything in the way of scientific instruments per se, but what it did have a lot of was instrumentation in the form of the control and systems panels. Keep in mind that a few things were moved, added, or changed to these panels over the course of Mercury's flights, but the vast majority of this should be pretty standard across all the Mercury spacecraft. As we get into the instrumentation cluster, starting at the center of the main instrument panel, we'll first go over the satellite clock. As I'm sure many of you who know Mercury are thinking, it was indeed the clock that is referenced when you hear Mercury astronauts do the whole "and the clock has started" thing. It was a spring-driven mechanical clock that would indicate such things as elapsed time from launch, time of day in relation to the Cape, time frames in which to fire the retropack, and would even be hooked up to ground control via telemetry to allow for a timed automatic firing of said retropack. In addition, the clock would also feature a nice little indicator light that would light up 5 minutes before its retrograde burn, and was aptly labeled the "time to go" light. Looking to the left of the satellite clock, we would have this cool little moving map called the Dead Reckoning Earth Path Indicator. It was completely spring-driven and required no electrical power to function. Inside of it was a fully gimbaled globe of the Earth that could be adjusted by knobs to correct for drift, correcting this drift by the pilot using measurements gathered from the periscope. Speaking of that periscope, it was a true OG periscope that was optically based using lenses and such. It could be extended or retracted in 5 seconds, and could be pulled out much like a car's steering wheel by its pilot to better see through its 8-inch diameter non-reflective viewing glass. It would feature a magnification range of 175 degrees all the way down to just 19 degrees field of view. I could go on forever about the periscope, like how we got this sick looking video when they put the camera on it for Ham the Chimp's flight, but to keep it short, a few other notable features were built-in color and sun filters, a sun-moon index ring, and manual mechanisms for both periscope retraction and periscope hatch door closing, with that little hatch door being this little guy as well. Slightly to our left in the center panel would be our accelerometer, reaction fuel gauges, descent rate indicator, and altimeter. Capsule 16 documentation also shows what looks to be an onboard camera timer of some kind here. Don't know if it counted up or down, but it was most definitely used to judge camera use by seeing how much film was left or taken. You get what I mean. Moving up to the very top of the center console, we'd have your classic aviation pitch, roll, and yaw indicators. The attitude section of this indicator would be fed from inputs from the Automatic Stabilization and Control System, ASCS, while its pitch, roll, and yaw needles took inputs directly from the system's transducers. Now moving to the upper section of the right-hand side console, we'll see a cluster of indication gauges for such things as cabin, suit, and steam vent temperatures, as well as oxygen and environment pressures. Going on down, we'll come to our primary electrical system panel with all the readings you would want to know, alongside the corresponding controls for the main electrical systems. At the very bottom of the right side panel, we'll have the switches and mixing dials for the comm systems. On the far end of this panel, we'll first have our warning lights for the uh-oh moments, with the switch to turn on or off the compressed air-based blood pressure monitoring system. Switches alongside the warning lights could be used to mute the headset tones individually. In addition, the warning lights even had their own little dimmer switch. At the very last section of the right-hand panel was the three-way switches for such things as standby modes and bypasses. Before moving on to the left-hand side, one more separate console off to the side would also provide the emergency oxygen switch and levers to adjust suit, cabin, and inverter temperatures. Getting around to the left side panel, even though this is a tad bit long-winded, I hope that it comes across here that while being complex and daunting to look at from a glance, the vast majority of Mercury's displays and control panels could indeed be understood by everyday people like you and me. Starting from the top of the left panel, we got our big old abort signal light. Safe to say, definitely not a fun time if that lights up. Next, we got the switch to indicate to launch control that we are ready to go. After that is this water seal regulator. I'm assuming this is to cut off oxygen regulators from the main environmental controls, but it's there. So the next section of lights going all the way down was basically your status lights. Green for good to go, and red for not so good. Directly next to each one of these status lights was their respective handle, switch, or button to provide manual overrides. Finally, we get to our last instrumentation panel. Again, starting from the top, we first have our launch escape system and automatic retro pack jettison arming switches. After that, we have the fly-by-wire, and yes, that's a thing, and our ASCS mode selection switches. Right below that, we got our cabin pressurization controls, the retro delay switch, interior cabin and photo light switches, telemetry setting switch, and the manual override for parts of the rescue system. These remaining 4 push-pull handles would be for physically actuating the RCS system, with the handle labeled manual, adjusting between direct or rate compensated actuation. It should also be noted that these handles and much of Mercury's manual control systems were literally mechanical in nature, allowing for use even if electrically dead in the water. Finally wrapping up the control panels, there was the fuse switches located all the way to our left. Phew! Alright, so that's about all of the Mercury's control systems right there. There's only a few more left that we'll cover later on when it's more relevant, but for now we'll be moving on to the onboard cameras. Although 35mm cameras were used on Mercury Atlas 6 and 7, the standard Mercury layout would see it being fitted with 2 cameras, the Astronaut Observer camera and the Instrument Observer camera. Both of these cameras would use a 16mm polyester-based film known as Chronar, or Chronar, whatever it is, produced by DuPont. Starting with the Astronaut, or dare I say, the selfie cam, it would house a total of 250 feet, or 10,000 frames of film. It and the instrument camera were both capable of a high and low speed setting, with a built-in programmer able to change these settings within a range. Oh, and about that FPS range. Yeah, the selfie cam was capable of between 1 frame per 16 seconds, and went all the way up to a whole whopping 6 FPS. The instrumentation camera was about the same when it came to frame rates, still keeping that speedy 6 frames per second, while only going down to 1 every 10 seconds for some reason. Joking aside, these cameras were super small for the time, and pretty damn cool. with both cameras even having their own little mechanical clock to show what time each frame was taken. Just a little fun fact about the camera clocks. They would use an even smaller light bulb to illuminate the clocks for clearer viewing by the cameras, and would also turn off briefly at T0 to indicate launch time when reviewing footage. Specific to Sigma 7, or Capsule 16's mission, Wally Schirra would also carry up a 70mm handheld Hasselblad 500C camera, somewhat starting the whole NASA and Hasselblad thing. In addition, there was also 4 photo recorders for measuring cosmic rays. I'm pretty sure this was simply just film strips with covers on them to prevent unwanted particles. I don't know where they're located, but they exist. Also, I should mention that other capsules did have a window observation camera like those seen on Al Shepard's flight, and were basically identical to the previously mentioned cabin cameras. Lastly, and kinda being an instrument I guess, Mercury had this magnetic tape recorder right here. It recorded both comms audio and telemetry data. Nothing too crazy about it, but it's a thing. Anyways, time to start covering them fuel and propulsion systems. Getting into Mercury's propulsion system, we'll first go over the fuel and helium tanks. Each being these half-toroidal curved cylinder-looking things made from aluminum, both of Mercury's fuel tanks would consist of a small perforated pipe going down the center of it, with a bladder lining the inner surface of the cylinder walls. Being fed helium from the helium tanks at 480 psi, this bladder would make sure its fuel stayed together even under zero-G conditions. Each fuel tank would also be given priority to certain onboard systems, with one tank being used for the automatic system and the other being used for manual control. However, interlinks between the two tanks was possible via more piping and an override system. Continuing on to those helium tanks, the 2 fiberglass helium tanks would be placed right here behind the control panels. Each would be pressurized to an impressive 2,250 psi and would be used only for fuel tank pressurization. Moving on to the main means of propulsion, it's time to go over the reaction nozzles. Just like the Redstone's rocket's gas generator, all of Mercury's reaction control system would use H2O2, or hydrogen peroxide, as its fuel source. Being a monopropellant, this hydrogen peroxide was extremely safe, and while not impressive as far as thrust numbers go, the relative lightness of Mercury made it a solid choice. After snaking its way through unchanged, this hydrogen peroxide would finally end up going through the thruster's catalysts, making a 90-degree turn and then rushing out the nozzles. Now, about those catalysts. They would consist of the main bed here and these little sections called the cups. In essence, and this is my favorite part, these would use a series of compressed metal screens plated with silver. When the hydrogen peroxide hits these screens, a chemical reaction breaks down this H2O2 into oxygen and superheated steam, making Mercury, in all technicality, a steam-driven spacecraft. Toot toot and all aboard indeed. With this expanding steam, we would see Mercury being fitted with 3 different levels of thrusters. 6 little 1-pound thrusters, 2 6-pounders, and these 4 24 pounds of thrust big boys. All of these thrusters could be commanded by electrical solenoids via the E.C.S, with the lower power jets being used for manual stick control. Just as I alluded to before, the manual control nozzles would be fitted with their own check valves to allow for a mechanical direct override of stick control through the previously mentioned instrumentation handles. Next up on the list is one of the more striking and obvious features of Mercury, the retro and posigrade pack. Both systems would be incorporated into the pack and would both use solid fuel. First, we'll start off with the posigrade rockets. Technically being kick motors and functioning as the main separation device between the spacecraft and its missile adapter, these 3 Atlantic Research Corporation rockets would each produce 370 pounds of thrust for a period of around 1.3 seconds. It was fired automatically when given a signal from the capsule adapter sensor after explosive bolts on its clamp ring had been detonated. In between the posigrade rockets is where we would find our proper retro rockets. Each of the Thiokol-produced Model TE-316 retro rockets could produce an average of 968 pounds of thrust for 13.3 seconds, slowing down Mercury just enough to dip it into the atmosphere. To keep the rockets nice and warmed as they like to be, electric blankets combined with that iconic striped black and white thermal paint would provide temperature control via thermostats and its own temp controller. Another couple factoids I find interesting about the retro pack was 1. The retro firing could be done by the satellite clock, by ground command through ground controllers and decoders, or by pilot override mentioned on the control panel. And number 2. The straps of the retro pack were held on only by tension. However, a large explosive bolt in the center of the pack and connected to the spacecraft held it firmly in place. Normally this bolt would fire automatically, but luckily for John Glenn, the auto retro pack arming switch could be switched off to negate this. This rarely mentioned technical detail is almost undoubtedly what saved John Glenn's life. I want to highlight this and many other small details in this video to drive home the sheer amount of hindsight and thought put into Mercury's design. Just about everything that could go wrong on this thing had some way, if not a few ways, to deal with any given problem. And while I know it's a lot and that this video might drag on at points, it's important to showcase the lengths these engineers went through to make Mercury as safe as it could possibly be. Speaking of that safety, this is a perfect segue into what some would call Mercury's safest rocket, the LES, or Launch Escape System. Being another of Mercury's more memorable external features, we will divide the LES into 3 basic sections: the adapter, the pylon structure, and of course the rockets. The LES adapter did what you'd expect. It would feature the clamp ring used to separate the LES from the capsule, and would house not only 2 different separation mechanisms, but also the wiring needed to indicate separation has occurred to time relays in the LES. Moving on up, we'll come to the pylon structure. Being constructed from sturdy, diagonally braced tubular steel, the pylon could withstand all abort conditions and would also be what the antenna fairing and horizon scanner covers were mounted to. Getting around to the star of the LES show, we'll go over the not 1, but 2 rockets on the LES. First, of course, is the escape rocket. This big old solid-fueled monster could produce an incredible 52,000 pounds of thrust for 1.39 seconds. Made by the Grand Central Rocket Company, internally it would feature the distinct star pattern that solid-fuel rockets would use up to this very day, producing an even burn as fuel was expended. As we can see in this documentation, while having 3 nozzles, the escape rocket is in fact just one big burny boy. However, to make sure it does its job, thrust to all 3 nozzles must be aligned perfectly. There's just one little problem though. Having no gimbaling capability and being solid-fueled, one could not test this beforehand or align the rocket while being disassembled. To accomplish this task while the rocket was in one piece, down at the bottom of the rocket would be this target and mirror arrangement that was used to literally eyeball this alignment through a little sight glass. The second rocket system, the one that goes quite unnoticed unless you look very closely, was the LES jettison rocket. This little guy could produce 642 pounds of thrust for a period of 1.67 seconds. It would be used, as the name implies, to jettison the LES tower away from the capsule after the firing of its escape rocket and being triggered by our good old mechanical friend, the timed relay. In addition, the top of the LES is where its aerodynamic spike was located, as well as around 230 pounds of ballast used to help chuck the capsule over itself. From a firing at ground zero, the delta V imparted by the LES could propel the Mercury capsule to an astonishing 2,200 feet above and out of the way of the launch pad. While not being propulsion in the terms of moving the spacecraft, Mercury also had quite a few pyrotechnic devices. I won't go over every single one of them, but I'll list them here just in case anyone wants to pause the video to go over them. Now let's move on to spacecraft navigation and control. Before starting this section, I just want to add that for time's sake I won't be going that deep into event sequencing or programming for Mercury, but it is insane and completely done via analog means. So if you do want to check that stuff out or go deeper into these systems, feel free to check out the documentation linked in the description. With that said, let's dive into our first set of navigation features, the horizon sensors and the gyroscopes. Starting with the horizon sensors, There were 2 located inside the antenna fairing, and yes, both of these would indeed be yeeted away into the Atlantic with said fairing after deployment of the main parachute. There was one for roll and one for pitch. These scanners would take in the horizon light through means of a motor-driven rotating prism spinning at 30 RPM. Both could scan a conical area of 118 degrees and would, to the best of my knowledge, output a DC signal to add reference for and counter drift in the ASCS's gyros by adjusting or torquing the gyros. Speaking of the gyros, Mercury had a total of 5. These would consist of pitch, roll, and yaw rate gyros, as well as vertical and directional attitude gyros. In addition to this, there was also a longitudinal accelerometer set to signal out at 0.05 Gs to automatically initiate the ASCS's reentry mode. Now we are going to talk about one of the things that got me really excited to do this video, Mercury's control systems, and we'll start with the big one, the Automatic Control and Stabilization System, ASCS. The name says it all as far as function goes, and from taking measurements from the gyros and the accelerometer, the heart of this system that allowed it to do what it did was this bad boy right here, the calibrator amplifier. I will be the first to admit that some of this thing is way beyond me. However, while I don't quite fully understand the programming of the so-called cal amp, I do have the basics down. The first and craziest thing about the cal amp was that it had a logic system using absolutely 0 digital systems. Similar to like an old elevator or something, this thing was mostly just logic relays and control relays. It would provide automatic control using what's called RCL, or Relay Control Logic. This picture is about the closest thing I can find to simply explaining what RLC is, but it would be a super complex version of this that would allow Mercury to control itself to such a large degree without digital logic. There were a few transistors and diodes here and there, but these were simply just switching circuits, and the vast majority was relays. Lots and lots and lots of relays. For those of you in various industries, these would be indeed very similar to what you would see in a PLC, just without the P part, as it would not be reprogrammed in the same way a PLC could. The ASCS would have 4 primary sections, so to say. Slaving, aka resetting the gyros using the horizon scanner. Repeating, used for rate and spin functions. Mode switching components. And the torque switching section used for thruster firings. Its inputs and outputs use things like a fluid-filled acceleration switch and servo mechanisms for the attitude gyro. The ASCS system had 4 automatic modes selectable by the pilot. The first one was the damper mode, used to maintain or stop spin rates. Next is the orientation mode, used to hold position. Third was the attitude hold mode, used for exactly what you'd think it'd do. And finally, the re-entry mode, used to keep Mercury exactly how it needed to be when coming on down. In addition to this, the ASCS would also feature a fly-by-wire mode, allowing flight stick control through the ASCS via limit switches. Getting around to that flight stick in the primary manual control system, we have to talk about the RSCS. Being similar in concept to the ASCS, but being the manual version, so to say, the rate stabilization and control system would function independently from the ASCS, include its own mini gyros, and would receive inputs from the flight control stick through the means of potentiometers. The RSCS could also provide its own rate damping capability as well as provide a constant roll after the re-entry G sensor had been triggered, effectively adding a backup redundancy in case of an ASCS failure. But Ben, you might be asking,
what would happen if the automatic controls went out?
Well, backups, checks, this would not happen.
I said, what would happen if it did?
Okay, fine. As we can see in this documentation, there was literal flight control linkages like you would see in an aircraft all up in this thing. This was primarily to reach the proportional valves used for the mechanical control system. And just in case all those previously mentioned systems failed, or being in a power out situation, this system would allow for direct control over the spacecraft. Even in the case of a stuck valve, them clever engineers got that covered as well. Located on the flight stick was a little soft aluminum pin. This pin was designed to shear off by yanking the ever-loving shit out of that handle. thus giving the pilot full and forceful manipulation of the thruster valves themselves. This last system was the backup of the backup and the absolute last resort for spacecraft control. With that in mind, I want to stress that even the best pilots like the Mercury 7 are still human, and that even with the best training, the workload required for Mercury made its automated RCS systems actually quite a welcome feature over time. So, while not quite being proper navigation or a control feature per se, this is a good spot to mention the parachutes. Mercury had 4 of them on board, and unlike Apollo's triple mains, Mercury's would all be single parachutes. They were the drogue chute, the main chute, and the pilot and reserve parachutes. All would be primarily made out of nylon, and would be categorized as just drogues and mains. We'll start with the drogues. Consisting of both the main drogue and the pilot parachute, both would be 6 feet in diameter, with the pilot chute being used as basically the drogue for the backup reserve parachute. The only main difference was the drogue was used to slow down the capsule from around 40,000 feet and would be contained within the antenna fairing, while the pilot chute was mainly just for bringing out the reserve parachute and would be placed within the capsule. At around 10,000 feet, a set altitude device known as a barostat would trigger and do a bunch of things. Open the cabin air inlet and outlet valves, fire the antenna ejector gun to detach the antenna fairing, but would more notably fire the gas cartridge used to rapidly fill the main parachute's ejection bag, deploying said main parachute. The main parachute for Mercury would measure 63 feet in diameter, and could slow the now lighter 2,100-pound capsule to a speed of just 20.4 miles per hour. The last thing about navigation mentioned would be the navigational aids. Below the periscope in this little baggie would be mission reference materials such as note cards, stereographic maps, and even a pencil. That's right, even though I love the whole NASA made a fancy pen while the Soviets just used a pencil joke, it is with the navigational aids bag that we finally know it was truly just a joke. The Mercury spacecraft would use a total of 9 different radio systems. And to preface this, I must add that UHF frequencies were a tad bit different back then. So if you hear some numbers that we would technically see as VHF today, this is why. Getting into the orbital voice communication system first, we'll see a two-way system with both HF and UHF capable transmitter-receiver units, both using AM or amplitude modification. The HF system operated at 15.016 MHz and with an RF output of 5 watts. While having a somewhat low output, sensitivity of this unit was insane, requiring no more than 5 microvolts to obtain a 10 decibel signal-to-noise ratio. The orbital UHF system ran at 296.8 MHz and having a power output of 2 watts. The main UHF system as well as the backup UHF orbital system would be identical, save for the exception of the backup using its own 0.5 watt transmitter. The high and low power settings on the control panel would allow for switching in between the main and backup orbital UHF radios. It should also be of note that both the orbital HF and UHF systems would also use the antenna fairing itself as a bicone antenna, giving the fairing its name and powering down these systems after fairing jettison. Getting onto the main radio beacons, Mercury's S-band and C-band beacons would both provide adequate radar tracking of the capsule at all times. Both systems having a nominal range of 998 miles from orbit, they were also double pulse coded, transmitting 2 quick radio pulses as to distinguish the signal and reduce interference. The S-band beacon transponder would broadcast at 2.84 GHz, with its transmitter operating at 2.91 GHz. It had a peak power output of 1000 watts or 1 kilowatt, and could be acquired by both the SER 584 Mod 2 mobile radar, as well as the advanced long-range Verlort radar system. The C-band beacon would both have a transmitter and receiver. The transmitter ran at 5.55 GHz, with the receiver using a 5.48 GHz frequency. The C-band beacon would have a peak power output of 375 watts, and was specifically designed for use with the extremely accurate AN-FPS-16 single object tracking radar. Both the S and C band beacons shared their own set of 3 flush helical antennas placed around the capsule to provide constant tracking even while Mercury was being spin stabilized. Shortly before and after splashdown, this was where the recovery and rescue radio systems would come into play. Firstly, we'll get the HF comm system out of the way. It was basically the same as the orbital system, however it used a lower power output of 1 watt and would be fed through the isolated electrical system. Next up is the HF and UHF rescue beacons, with both being housed in the same module and both using PM or pulse modulation. The HF portion of this system utilized a portion of what is called the C-Save beacon. I looked it up and have no clue what it stands for. Hopefully somebody in the comments knows what's up with that, but it ran at 8.364 MHz. The 243 MHz UHF beacon, on the other hand, will be the first of a few beacons in Mercury made by the British company Ultra Electronics. They were known as SARA beacons, standing for Search and Rescue and Homing. All of the SARA beacons that will be mentioned in this video will all have a line-of-sight radio range of no less than 100 miles, or 160 kilometers. While we are on the subject of SARA beacons, we'll get into the UHF auxiliary beacon known as the Super SARA. It was used primarily for establishing contact and tracking with the airborne rescue crews, mainly those planes you see them launching off the aircraft carriers. They received power from the standby system and would run at 243 MHz, having a peak power output of 90 watts. With the antenna fairing being thrown into the abyss, the HF rescue comm system as well as the HF radio beacon would use this now unstowed whip antenna and would just pop itself on out. Documentation also says this thing was 16 feet long, and turns out it is. While not seen in a lot of footage, right after the recovery crews find the capsule, it can be seen extended, and it is indeed a long boy. The rescue UHF alongside the aux UHF systems would both use this crazy looking butterfly antenna, which would also flip out after fairing jettison. This butterfly antenna would also be used for the backup UHF comms, the command system, and the system we will get onto next, the telemetry system. The telemetry transmitters for the Mercury spacecraft would use both a high-power system and a low-power system. The high-power system ran at 259.7 MHz with an output power of 3.3 watts, with the low-power system running at 225.7 MHz and with an output power of 1/6 of a watt. Using the main electrical system and individual transistorized power supplies for reliability, both of these telemetry systems were actually completely identical units, with the low-power system only needing a little bit of tweaking from ground crews to obtain both a different frequency and its low-power characteristic. I unfortunately could not figure out how much data these could put out, but for those ham guys and radio people out there, I do know that it used 6 separate FM subcarriers, with one of them using pulse amplitude modification on the 10.361 kHz subcarrier frequency. Also, we do know that the low-power system provided 88 data samples and 2 sync pulses every 1.25 seconds. The low-power system was capable of 4.5 hours of operation while the high-power system ran continuously. Both telemetry systems would also remain running for 10 minutes after touchdown. I know, lots and lots of radios. But luckily we arrive at the last radio device inside the Mercury capsule, the command system. It does what you're probably guessing, send and trigger commands in case the pilot became unresponsive, or if ground crews noticed that something was not looking so good. It would consist of 2 frequency modulated command receivers operating at 414 MHz and going through 2 command decoders that were on board. Each command system could provide up to 20 decoder output channels, with 10 channels in the receivers and 10 in the decoders. These command systems were also quoted as being similar to the ANDRW-13, a system that was used by the early Saturn launch system. It is unclear if this system made it all the way to the Saturn V, but I guess we'll have to just wait for me to finally go into Apollo to know that one. Anyways, the command system would see it having 5 primary commands it could decode. Abort, retrograde ignition, which by the way would make the E.C.S automatically go into reentry mode, S and C band beacon activation, satellite clock reset, and a command to zero the instrumentation devices. Now, I can't leave the subject of radio systems without mentioning two things: the MSFN and the IBM 7090 mainframes. The MSFN would stand for Mercury Space Flight Network. It comprised radio comms, command, and tracking stations located at around 18 places all across the globe. Two of these would be stationary ships in both the Atlantic and Indian Oceans, and many of these installations would feature redundancies and backup systems. As some of my returning viewers have noticed, some, but not all of these ground stations would also house the systems for the satellite control network used by the Corona optical spy satellites. Alright, so the very last thing with comms and pertaining to the telemetry system was that IBM computer. Being a fully transistorized version of the then very popular IBM 709 mainframe, it was around 5 times faster than its vacuum tube-based older model. Just for context on how big of a leap this was, the 709 could do 42,000 adding or subtracting fixed point operations per second. While sounding like a fairly large number, the 7090 could do this at over 208,000. The best part is, while being much faster, the 7090 could be rented at less than half the cost of the 709. NASA would rent 2 of these 7090s, for redundancy of course, and would place both of them at the Goddard Space Flight Center located in Greenbelt, Maryland. So I'll cut to the chase and get to the cool reasons why I'm mentioning some big-ass computer mainframe in a Mercury Capsule video. 2 reasons, in fact. 1. The mainframe could drive that dope-ass physical map display thingy you see in Mission Control, from the indication lights on it, all the way down to the little capsule prop thing that would move across the map. And my second reason, the more important one, the IBM 7090 can compute any and all the trajectory necessary for an emergency reentry landing in only 30 minutes. This would basically allow for some quick maths to not only be done right at the sign of an emergency, but would also give an optimal time frame to hit the next ocean, so to say. As we can gather from the 7090 being 5 times faster, the 709 would take over 2 hours to do this very same task. For those new to the channel, this is what I like to call the special feature section of the video, where we go over the more unique features of a given craft. For Mars 3 it was the OG Martian rover, for Surveyor it was the little scoopy arm thing, but for Mercury it will be something we haven't covered on the channel yet: life support. I will also be grouping a few devices in here that, while not being life support per se, were still just as necessary due to the human aspect of Mercury. Now let's dive right into it. First we'll cover the big stuff: the spacesuit and the E.C.S, or Environmental Control System. Starting with the spacesuit, it was made by B.F. Goodrich. It would be pressurized to 5 psi, weigh 22 pounds, and would be comprised of 2 layers. With the pilot wearing long underwear for comfort, the inner layer of the suit would be made from neoprene and neoprene-coated nylon fabric, with the outer layer consisting of the aluminized nylon fabric that gave the suit its famous metallic silver appearance. Its fiberglass helmet would feature a plexiglass visor that would, at least with the older suits, be pressurized via air pressure from its own little visor sealing tank seen here. The Mercury Goodrich pressure suit would also be air-cooled from the E.C.S system through a duct near the astronaut's waist, and exiting out the tube nearest to the helmet. This now heated and CO2-laden air would then be recycled out of the suit and back into the E.C.S, and I think it's about time we talk about it. This crazy-ass series of tubes and boxes is the E.C.S. While having adjustment controls, the E.C.S is fully automated and can run without pilot intervention. I won't go into every nut and bolt and valve on it, but we'll talk about the main primary components, starting with the oxygen supply. Being stored at a massive 7,500 psi, but then being dropped down to 100 psi for the rest of the system, 2 tanks located here at the very bottom of the E.C.S would provide a primary and backup breathing source, with the secondary or emergency oxygen intentionally lowered to an output of 80 psi. Each held 4 pounds of oxygen. There looks like there was a plan to actually use a third smaller oxygen bottle just for cabin pressurization, but from what I've researched, this has never made it to production capsules. Oxygen to the suit as well as the cabin was kept at 5 psi to simulate oxygen intake here on Earth and to avoid oxygen toxicity. As oxygen from these bottles was introduced into the pressure suit air loop, it and used up air would pass over the odor and CO2 scrubber. Being housed in these two rolls, the scrubber would use charcoal for odor absorption and lithium hydroxide for CO2 capture. Right after used air exited the spacesuit, it would first go through the solids trap. As one would expect, this thing caught hair, food particles, and my favorite, nasal excretions. NASA's words, not mine. Making our way past the solids trap, we arrive at the two suit fans. They are indeed fans, but more importantly, they are compressor fans, forcing that air on through all good-like. After passing by the compressor fans, we get to the 1000 BTU rated suit heat exchanger. So this is probably a good time for me to mention Mercury's cooling system. I've kind of been saving it for this section as it's pretty damn clever, and mainly used for life support. So in orbit and re-entry, Mercury was completely water-cooled. This water cooling loop consisted of a bladdered water tank compressed by the oxygen system, and would flow through both the cabin and suit heat exchangers, in addition to the previously mentioned AC inverters. Now most of you, like myself, are definitely not engineers, and might be wondering just how the hell did they get that amount of heat transfer out of a water-based system. As a certain Anakin Skywalker used to say, this is where the fun begins. Notice how on this diagram, it has a bunch of valves right until you get to the very bottom of it. Yeah, that's because the end of this cooling loop is completely exposed to space. As water from the coolant tank is slowly released via the control valves, it will hit the vacuum of space, and as you can guess, it's one big-ass vacuum. I did some math on this and found that the low Earth orbit Mercury used would drop this water's boiling point to around negative 247 degrees Fahrenheit, immensely improving its evaporative and heat-conducting properties. The very second this water hit the fabric-based microporous heat exchangers, it would almost instantly flash to steam. In fact, to make sure this exiting steam did not freeze when being vented overboard, it was ran back through the hottest part, or the front, of the heat exchangers, making true superheated steam. I cannot understate just how insanely clever this heat extraction method is. Yes, we are using up this water as we go, but due to the sheer efficiency from how much vacuum is being pulled, this would be a trickle of water, if not drops of water at a time. The single relatively small coolant tank lasted the whole 6-orbit, 9-hour duration of Capsule 16's flight. I should also note that, without the vacuum of space present, landing and post-landing cooling was accomplished by using some nice cool and salty sea air through the means of air ducting directly to the compressor fans, and by this thing, the snorkel. It had its own explosive door and featured valve work to block water ingress. In addition to cooling, this natural air would also take over as a landing and post-landing oxygen supply. Through the launch phase of Mercury's flights, though, they would run Freon 114 through the exchangers from the ground umbilical connections, supercooling the system and kinda just letting it sit there and evaporate until Mercury reached space. Also, yes, this thing was also just freely venting Freon as it went up. It was a different time back then. Before moving away from the E.C.S, I just have to mention the water separator because I find it both ingenious and hilarious. Located at the very end of the loop, to remove excess humidity in the suit cooling and breathing circuit given off by the pilot, we would see this odd-looking contraption. It would absorb moisture via a vinyl sponge, and, as you can gather from this diagram, would use a time solenoid valve to drive 100 psi oxygen into a piston to literally wring the sponge out every 30 minutes, even squeezing this water back into a condensate tank to be used as emergency drinking water. How nice of it. Getting around to the last of our life support features, we'll dive into the more human touches Mercury required. After all, human beings needed things like a place to sit. They needed to be able to do things like see with their eyes. and needed interface controls that a human hand could use. First, there was the pilot seat and harness. The seat was adjusted for each individual pilot and featured a honeycombed fiberglass crush structure underneath it to absorb impact forces, especially if it ever came to a ground landing. The harness would do its thing as you'd expect, and the astronaut would use this release lever for egress from his seat when being recovered from the capsule. Next, we got another lever, the ultimate oh shit handle. Yep, it's the abort handle. Pretty self-explanatory, however, it should be of note that it did house the push-to-talk mic button on the side of it, as well as a button on the top of it which actuated a locking pin safety mechanism so one of the boys didn't pull a little whoopsie with it. Another built-in Mercury feature was its two doors, or hatches. Gotta get this guy out somehow, right? The first of this is the entry hatch, or the
Hatch with explosive bolts on the spacecraft.
As we can see here, while having exploding bolts, the explosives in this hatch actually lined and filled this inner channel all the way around it. So while the bolts did explode, they were not technically explosive bolts, and were in fact sheared off by the ring of explosives. Being fired via a non-electrical percussion cap like a plunger out of some old TNT detonator, it also featured an external handle for detonation by one very unlucky recovery crew member, because while the hatch was secured by two retention springs, it would still explode right out at the recovery guy if the external handle was used. The second hatch, also called the escape hatch even though they could both be used as such, would be located on the top of the capsule below the parachutes. Once touchdown had occurred, these things called the parachute mortars would fire and chuck them useless parachutes away. In the process, it would open up this little half-circle section of the capsule. Using the lever seen in this diagram, the pilot could open this escape hatch and be egressed from the spacecraft using the specialized arm harnesses carried by the rescue helicopters. While being a tad bit mundane, something that's not featured on my previous unmanned videos was, well, lighting. Firstly, the rescue guys gotta see this thing if it's nighttime, especially in an emergency. So thusly on top of the capsule featured one bright-ass strobe light flashing at around 15 flashes per minute and using its own internal battery system. Inside the cabin, the Mercury capsule would house a total of 4 lights consuming 4 watts each. They would use the dual AC system of the fans bus to power each of Mercury's 6-inch long miniature fluorescent tubes. 2 of these tubes were located above and behind the astronaut's head and were used for photo and camera lighting, nothing too special. The 2 other pilot lights, on the other hand, had a little bit more going on with them. Located in front of the pilot to his left and right, when initially researching this video, a few sources mentioned these as dimmable lights. I was sitting here going, man, in 1961 they really put variable ballasts, the device used to run the high voltage fluorescent lights, need, in this thing? In my ignorance, and doing later research, I realized that no, they meant actual physical dimmers. Each light had a little sliding shutter to provide the dimming, with both even housing a second slider with a red filter for comfortably seen in low light conditions. On the longer missions like those of our highlighted spacecraft Capsule 16, there's another saying that goes, a man's gotta eat. It was some of that good old early spacecraft toothpaste food, such as beef stew or applesauce, in addition to low residue freeze-dried cubes. The food was housed in a fairly basic metal tin in between the flight stick and the right side instrument panel, and safe to say, the astronauts didn't really like it all too much. There was one other thing that had some more food in the form of vacuum-sealed military rations, and that was the survival kit. The kit consisted of 3 major sections: a 2.5-liter water bag, a one-man self-inflating life raft, and the survival kit proper. The kit held just about anything the pilot would need in case he had to bail out of the capsule. The intro made it look fast, but it usually took around 3 hours for aircraft crews to arrive at the landing zone. So with the somewhat unpredictable weather of the Atlantic and the limited forecasting at the time, there was a very real possibility the pilot could drift away or encounter a developing storm, making it possibly days for a recovery. Luckily this never happened, But man, they were ready for it. First, the kit had desalting packets to make ocean water drinkable, from what I can gather using silver zeolite and silver dioxide to do so. It would also house a first aid kit with a gauze bandage, compress, a mucilin bandage, 6 meclizine motion sickness tablets, 15 oxytetracycline antibiotic tablets, and 3 auto-injectors. Info on what exactly the injectors used was somewhat difficult to find, but from what I've looked up, they would be such things as stimulants, pain relievers, and vasoconstrictors to negate shock. In addition to this first aid, there was also a tube of zinc oxide for wound sealing and treatment. The kit had various basic things such as a pocket knife, a whistle, 10 feet of multi-braided nylon line, some soap, and of course, some sunglasses, with the sunglasses even being kept afloat via a foam sponge. And yes, the foam sponge did double duty when it combined with the soap bar. There was a signal mirror, around 18 full-sized waterproof matches, dye markers to help aircraft spotting, and a proper full-size knife whose handle held extra matches as well as fish hooks for the mentioned nylon line. Oh, and yes, you are reading that right. There was indeed shark repellent. Developed during World War II and called Shark Chaser, even the capsule itself would house its own automated shark repellent system somewhere above the heat shield. The survival kit also had a flashlight. For all of you wondering, it was an ACR-4E flashlight, ACR being a US company that still makes lighting devices for the military and NASA to this very day. Fun fact, they also made the Apollo flashlights that were used quite extensively during Apollo 13. The final kit of the survival kit was the RB-7 Ultra Sarah beacon. It was self-contained, used an efficient low-power Morse code beacon, and had built-in voice comms to boot. Though I don't have this confirmed, it most likely ran at 243 MHz, the main distress frequency used by the military. The few last human-based things inside Mercury were a couple basic devices and the health monitoring equipment. For the basic stuff, there was another ACR-4 flashlight mounted on the upper left-hand side of the capsule, and mounted right on the entrance hatch was a NASA-produced knife for any emergency cutting needs. In addition, also mounted on the entrance hatch was what NASA called a canvas bag assembly with a waterproof inner bag assembly. Classic engineers, such a professional name for what is essentially a barf bag. As for the monitoring equipment, first there was a blood pressure monitoring system that would run continuously during launch and re-entry phases, with the little instrumentation switch we talked about operating it manually. Second, there was those infamous electrodes used to stream echocardiogram data to be plotted by ground stations. Third was a respiration monitor using what's called a thermistor, and also was attached near the microphone. So, the last piece of health monitoring equipment is one that, for dignity's sake, I was actually going to leave out of this video. However, due to the right stuff having some, uncomfortable scenes, everyone around me almost begging to mention it, and the fact this is Retro Rockets, I'm going to show it anyways, and just let the documentation do the talking on this one. Yeah, I know, there's a million jokes I could do with this one. But I'll just leave it with the fact that, not surprisingly, after Mercury, this system got phased out pretty quick. I will also note that Wikipedia and Google sources say that this was phased out during Mercury, but as we can see with our Capsule 16 documentation, which happens to be the second to last Mercury mission, this, was unfortunately not quite the case. Moving on from that thing, just a few quick mentions about Mercury that I couldn't really find spots for in the video format. One was that there was a cabin purge system that could extinguish fires and just emergency vent that shit. Pretty cool. Another was the other larger dye markers. One was underneath the reserve parachute and ejected with it, with the other one being placed above the heat shield somewhere. These would be what would give off that distinctive green coloring trail seen in photos and video footage. Being our spacecraft for the video, Capsule 16's flight, MA8 Sigma 7 with Walter Wally Schura, would feature a few highlights of their own. It would be the first to feature SOFAR bombs, basically a tiny sonar depth charge. One was ejected just prior to touchdown and was set to detonate at a depth of 3,500 feet, providing a backup location ping for tracking. The second one was what I called the whoopsie-daisy bomb. Permanently attached to the craft and set to detonate at 4,000 feet, hearing this second SOFAR bomb indicated to recovery crews that the capsule had passed the point where an ocean floor recovery of the capsule was possible. Well, at the time at least. As we know today, in 1999 and with better technology, Liberty Bell 7 would be raised from a depth of 16,000 feet. Sigma 7 was also another flight which saw the quote-unquote fireflies. Fine glistening particles surrounding the craft that were later found to be tiny bits of ice flaking off the hull. They originated mainly from the steam-based thrusters, and as we know now, some of it was probably caused from the near-zero velocity vents of the cooling system as well. The flight of Capsule 16 would also be the first to not use a helicopter recovery, with the USS Kearsarge aircraft carrier being 0.5 miles, or if you ask me, a little too close to Sigma 7 at the moment of landing. Wally would just ask them to just tow him to the ship. From what I've researched, this was totally unplanned, but I guess since he asked nicely, they just went with it. Like I said, it was a different time back then. After boarding the Kearsarge would be another good old unplanned Wally moment, where he told everyone to stand back and just blew the charges on the entrance hatch. As most die-hard Mercury fans know, this was specifically to be a true homie and prove Gus Grissom's innocence, as his hatch blew prematurely, causing Liberty Bell 7's sinking. Shira had to slam the plunger so hard that it ripped through his suit glove and bruised the hell out of his hand. Gus Grissom, on the other hand, was shown to have zero glove damage or bruising after he was recovered, clearing his name from the frankly stupid media drama that tormented him. On that note, I lastly want to briefly and respectfully dispel a couple things about the incredible film version of The Right Stuff. On the Gus Grissom hatch drama, while some of the media questioned if he accidentally blew said hatch, NASA themselves held firm and trusted Gus all the way. They always backed him up and knew full well a problem could occur. In real life, there was no such interrogation scene, and NASA immediately redesigned the hatch post-incident. Another small nitpick, and trust me, these are just little nitpicks, I have with the film is the capsule showing the press scene. Well, yes, I know it's hilarious, and trust me, that shit gets me every time, hence why I put some of the jokes in here. It somewhat detracts from the very real relationships these astronauts had with engineering and design crews. Not saying they didn't have a few debates here and there, or ask for a window, but for the most part, Mercury was a productive and collaborative team effort. Being somewhat portrayed as the hotshot fighter pilots in the film, the fact that these guys were extremely intelligent and well-educated is almost lost. They knew a lot more than the film lets on, and were much more friendly and hands-on with engineers than is shown. Other than that, though, the film, and especially the book, gets it spot on. Not only that, but it's one of the very few space race movies that was bold enough to show the brutal cost that often came with Mercury's fame and national pride. Many of these individuals sacrificed much of their personal lives in the pursuit of manned spaceflight, and both the book and the film do a fantastic job to not overlook this and not just tell the happy story, but the whole story. In the end, their story and bravery is nothing short of incredible. Everyone involved in Mercury, from the workers to the Mercury 7 themselves, are the definition of heroes. They pushed the limits of technology and helped lay the groundwork for all manned spaceflight systems to come. It would be no exaggeration that all of them, in fact, had the right stuff. Whew, there it is, the first American manned spacecraft. It was a lot of work, but I'm proud to say that I do this all myself. I'll never ask for your money, But if you'd like to support me, just do the whole like and sub mumbo jumbo to help the channel out. Thank you to every one of you supporting me, and as always, I'm Ben, this is Retro Rockets, and I hope you have an amazing day.